Okay, so first I just have some kind of motivation for why we're doing what we're doing. If we had a function like this, natural log of x over x minus 1. Clearly, can you just plug a 1 into this and evaluate it? No. So if I wanted to do the limit at x equals 1, we couldn't just plug in and evaluate. Now we've talked about a lot of strategies for problems when you can't plug in and evaluate. We've talked about factoring and reducing, but would anything factor and reduce there? No, we've talked about multiplying by conjugates, but that works usually when we have radicals, not so much in a problem like this. And so we need other approaches. We have done some, like if we were approaching infinity, where we would divide by the highest power of x, but we are approaching 1 here, so we wouldn't use that strategy. And if I'm looking at this, not only does the bottom equal 0, but what is the natural log of 1? That's like saying e to what power equals 1? 0. So this is actually of the form 0 divided by 0. And we can't say for sure what that is, because it kind of depends on which one's approaching 0 faster. And is one positive and one approaching from the negative, that kind of thing. So 0 over 0 is one of several indeterminate forms that we're going to be looking at in this section. Today, that is going to be one of the main ones that we look at, but as we go through this section, we'll talk about a lot of indeterminate forms. Forms where we can't just look at it and plug in and get an answer. So the only one we've done so far is infinity over infinity, like when we did those horizontal asymptotes. So that was an indeterminate form, and we divided by the highest power of x to work through that. L'Hopital's rule is going to help us with the others. And so what it tells us is that if you have two differentiable functions, and if you have an indeterminate form of either 0 over 0 or infinity over infinity, then we can use L'Hopital's rule. And what it says is that the limit of that quotient is the same as the limit if you do their derivatives. So our strategy will be to do the derivative of the top and the bottom. Now this is not a true derivative of the whole thing because we're not doing the quotient rule. We're just going to do the derivative of the top function, the derivative of the bottom function, and divide those. And it works out that the limit will be the same. Now, the only time you can do this is if it is 0 over 0 or infinity over infinity. Now we could do plus and minus, like negative infinity over positive infinity, we could still do it. But if you have a 0 over 0 or infinity over infinity, we can apply L'Hopital's rule. So here is my first example. The limit as x approaches 1 of the natural log of x over x minus 1. So that's the little example that I had at the beginning. You do need to check to see if it really is an indeterminate form. So if I just plugged in the 1, natural log of 1 is 0, 1 minus 1 is 0. So it is 0 over 0. What I want you to do when you do L'Hopital, I like you to just put like an LH over the equal sign so I know what you have done to get to the next line. Then the limit part stays the same, but we are going to do the derivative of the top and the derivative of the bottom. What's the derivative of the natural log of x? 1 over x, good. What is the derivative of x minus 1? 1. Okay, now, can we plug in? Yeah, if we just put in a 1, we get 1 over 1 minus, or over 1. So my final answer is 1. So this is helping us do limits that we cannot otherwise solve. Next example. The limit as x approaches infinity of e to the x over x squared. So first, check to see if we can just evaluate this. So if I plug in infinity, e to the infinity, what's anything to the infinity power going to turn into? Infinity. Over what's infinity squared going to turn into? Infinity. So this is infinity over infinity, which we can't do anything with. So we are going to do L'Hopital's. Make sure you're labeling when you do that for me. So the limit as x approaches infinity. What's the derivative of e to the x? Still e to the x. Derivative of x squared? 2x. Okay, let's see what we get if we plug in. E to the infinity is still infinity. 2 times infinity is infinity. Alright, so my problem hasn't gone away, but we can do L'Hopital's more than once. So it's still infinity over infinity, which is that indeterminate form. So that tells me we're still going to try L'Hopital's. Okay. E to the infinity is still derivative of e to the x, is e to the x. Derivative of 2x is 2. Okay, so e to the infinity is still infinity divided by 2, so it's no longer an indeterminate form. What's a really big number divided by 2? A really big number, infinity. I want you guys to try the next one. The natural log of x over the cube root of x. If you just plug in the natural log of infinity, and if you think about a natural log graph, it looks like this. So as time goes on, it's just getting bigger, so that's going to infinity. Cube root of infinity is infinity. So this is infinity over infinity. That's an indeterminate form. So that tells me L'Hopital's rule. Again, please make sure you're writing that infinity over infinity, first of all, so I know that you found it. And second, when you do the L'Hopital's, please label on that step when you do it. So we have the limit as x approaches infinity. The natural log of x, what's the derivative of that? 1 over x. Okay, the cube root of x, that's like x to the 1/3. So that would be a 1/3 x to the negative 2/3. Don't forget everything else that we've learned about limits. This is really kind of a mess, isn't it? So haven't we learned that sometimes a little bit of algebra helps simplify things a bit? Let's work on cleaning that up before we try to evaluate that limit. So 1 over x, okay, a negative power would put it on the bottom. How do you divide fractions? So this is like 1 over x times 3x to the 2/3 over 1. Okay, I have x's on top and bottom. Where do we have more of them? This is an exponent of 1. 1 is bigger than 2/3. So 1 minus 2/3 is a 1/3. So I have 3 over x to the 1/3. Okay, that is significantly easier to look at. Now if I plug in infinity, the top is going to 3, the bottom, the cube root of infinity, is infinity. So if you have 3 divided by a really big number, this is like what we've done before. Anytime you have a constant over infinity, what's it turn into? 0. So any limit laws that we've had up until now still work. Take the time to simplify things a little bit. It makes this significantly easier if you can cancel some things out. Is that okay with everybody? Let's do a couple more. Alright. If I just plugged in 0, tangent of 0 is 0, minus 0 is 0, 0 to the third is 0. So this is currently 0 over 0. If it's 0 over 0 or infinity over infinity, that's indeterminate, and we do L'Hopital's rule. Alright, what is the derivative of tangent? Secant squared x. Minus, what is the derivative of 1? Or of x, excuse me. 1. What a surprise. Over derivative of x cubed is 3x squared. Alright, if I plug in secant of 0, so that's the reciprocal of cosine. Cosine of 0 is 1, so that's 1 minus 1, so 0 over 0. So what should we do? Let's try L'Hopital's again. Derivative of secant squared. Okay, keep in mind, that's like a secant of x squared. So the 2 comes down, inside stays the same, subtract 1 from the power, so it's just the first, times the derivative of the inside. What's the derivative of secant? Secant tangent, yep. I couldn't resist putting one ugly 1 in here and seeing how much we remembered about all of our derivatives. Over, minus the derivative of 1 is just 0, so you could leave that part off. Over derivative of 3x squared. So if I clean that up, 2 and 6 would reduce. Secant times secant tangent would be secant squared x tangent x. Okay. If I just plugged in derivative or secant of 0 is 1, tangent of 0 is 0 over 0. So it's still 0 over 0. So technically, I could do L'Hopital's again, but the top is getting uglier each time, isn't it? Because when I have all these trig functions, those derivatives are not pretty. So it is a possibility and it will work, but it's just going to make the top uglier. We still have all of our other strategies that we can use. Keep in mind, secant is like 1 over cosine. Tangent is sine over cosine. Okay, I'm going to show a lot more work than maybe you necessarily have to here. But you could rewrite this as like 1 over cosine cubed 1 over cosine cubed, that's secant cubed. I am just going to put the 3 with this and the x over here, kind of pulling this away. Alright, this is an old trick. The limit as x approaches 0 of sine x over x. That one was just one of those theorems that we just knew what that turned into. Do you guys remember what that was? That's a 1. So, this sine x over x would turn into 1. If I put my 0 in here, secant of 0 is 1. 2 to the third is 1 over 3. And we get 1/3. Alright, I know that one was an ugly one. Probably a lot more than I'm going to give you right now. But I couldn't resist reviewing some of those derivative of trig functions and that sine x over x thing. So it was a good example to pull in a lot of old stuff. Okay, we're going to do one more and then I'm done for today. Last example. The limit as x approaches pi from the left of sine x over 1 minus cosine x. You guys miss trig, don't you? So, think about pi is like right here on your unit circle. Right? That's the point, -1, 0. Cosine is the x and sine is the y. So, sine of pi is 0. Cosine would be -1. This is 0 over 2. Can I do L'Hopital's? Do I need to do L'Hopital's? No. 0 over 2 is 0. So don't use L'Hopital's if you don't have to. Okay. Any questions for me? That is today's stopping point. And you guys have some time right now to start working on these. I did give you all odd problems so that you can check yourself and make sure you're doing okay, but you have to have work, okay? Not just a final.